So let's begin from where we left yesterday. One small announcement. Anybody who has not asked the question yesterday, definitely try to ask at least one question. So just a quick recap, which what we are trying to do. Just keep this. Just keep in mind what we are trying to do. So let's try to follow your recipe. What was that? What your mom competitive ratio of any randomized element. And what our recipe was, right here is division equal to star. The numbers on your records, the value Q. So Shruti could type and see. Hopefully that will be clear. What was star? Some specific quantity. Star was. Essentially, A star achieves star online or optimal deterministic online algorithm for input distribution. Very important. And this holds for any queue. So what we are going to do now is to somehow use this, find a lower bound for the key rental problem. Just to belabor the point, this is only giving you a rough idea what is happening. It's not telling you what that queue, which is a good candidate, neither is telling you once you freeze the queue, what is the optimal deterministic online algorithm. So both these questions remain open. All right, so let's embark on. So what we want to show, mu r is greater than t goes to infinity for any randomized. The size okay? Should I write slightly bigger? Okay. This is what we want to put. So two questions we have to essentially find a good Q and an optimal A star of Q. That's what we should be doing. We'll do this in a roundabout way. I don't know what a good Q is to begin with. We'll do this in a roundabout way. So let's start writing. Also remember the input is just parameterized by the length of my skiing interval. So this is a one parameter problem. So what is the expected cost of OPT for any Q? Is simply the expected value of min of L comma so I can write this as L equal to 1 through P minus 1 L times probability. So this is under Q plus P times probability. For anything, for any L between 1 and P, the cost is little l, and for anything over and above capital T, it is just capital T. This can also be written as probability. All these probabilities are under Q, so I'm not going to write again and again. All right. Now comes the more interesting part. All possible. Where remember, A subscript k is a deterministic algorithm which waits until k minus 1 days and rents until then and buys on the kth day if the season is still going on. And we argued yesterday that going beyond p is not useful. So we can restrict our attention to a1 through a capital P. So let p1, p2 be the probability with which a randomized algorithm picks these deterministic algorithms. So what is cost of AI? Okay. So if capital L takes value little l, then the cost of my algorithm AI, which runs until I minus 1 days, is L. If L is less than or equal to I minus 1 and I minus 1 plus capital P otherwise. This is condition. So there is no expectation, right? I'm conditioning on the fact that the skiing season is of length little l. Then what is the cost of this particular algorithm? I'm going to take the expectation very soon. So the expected cost of CAI. Again, all these expectations are with respect to Q. Summation. One. All right. I'm just writing this and taking the expectation with respect to the distribution. Now this can be written as, this is a simple exercise. You can rewrite this as simply plus just this term. It doesn't look obvious, but it's just a rearrangement of these terms. What I'm doing is I'm pulling this I minus 1 into this probability and adding it to it and just rewriting in a different form. Okay, so now we are at the place where you have to make some choices about the distribution and for a given distribution, how to find the optimal deterministic algorithm. See, all my deterministic algorithms are indexed from A1 through AP. That's all I have. Now, does it appear a simple exercise to choose a Q and somehow find this bound? Just stare at it for a while. So now we're at the place where you have to make something. You have to make a choice for Q, and for that choice of Q, somehow find out what is C star. So any idea how to go about that? For a Q, for a given Q, what should I do? How should I choose Q? Q essentially for the moment is just choosing capital L. That's the only random variable. Sorry. Geometric and computable. Okay. Good choice. Okay. What else? Say this again. No. OPT, I don't have a handle. So what could be one possible way of doing this? If you don't want to insist on finding a Q, think of one way I can accomplish this task without prescribing this Q, but I still want to compute this minimum. Think of something like there exists some Q for which something happens, which is sufficient for my task. What are all possible algorithms? Only A1 through AP. And what is my task? Somehow that I choose a queue and suddenly I'm able to compute C star. So can you think of a way where I don't have to specify queue ahead and say there exists a queue which satisfies something and which is sufficient to compute C star? I'm writing cost of each of these algorithms, right? So suppose there exists a queue for which expected cost of all these algorithms is equal. Let's suppose that happens. Then am I done? Is the premise clear? Suppose there exists a queue for which this expected cost for each of these algorithms is identically equal. Then this is a simple quantity compute because minimum is all of them are equal, so any one is fine. So now does it help us somehow? That can you think that should there exist such a queue for which the cost of all these algorithms is the same? Is the broad idea clear? That's more important. I'm asking for too much to begin with. There is no guarantee that such a thing should even exist. But supposing that exists, my job is very easy. Then I don't have to work hard in computing the minimum because all of them are equal. So now think about, should there exist such a queue? And the simplest thing is to just plug and play. That if it does exist, I should be able to equate this cost with the cost of CAI plus 1 for any I. And if I get a non-trivial solution, that is my queue. So that's what I'm going to do now. I'm just going to equate two costs. I'm not making any particular choice of I, so this is general enough. If I had said only A1 and A2, then it's not true. I'm saying for any I, this should be true. A1, A2, all the way to A3. So now I have an expression. All I need to do is to just plug and check if such a distribution exists or not. So left hand side is just P of. Now it should be, just by staring at it, you should be able to guess what the distribution should look like. What should Q look like? Just stare at this. I'm going to do the grand work here. Should tell you something. What should the distribution look like? All I need to do is to equate these two things together. Does it pop out directly? What should the Q look like? All I'm saying is what is the distribution of P capital L equal? Q is nothing but probability. That's all we are interested in, which satisfies this relation. Anyone wants to guess what that Q should be? You can kill some terms out here. What remains? So this is equivalent to P times probability I. Very nice recursion if you think about it. Beautiful recursion. All these terms are in just CCDF of L. Term involves I, this term involves I plus 1. Can you just give me one choice which satisfies it? Now this is like this. Must have seen this relation before. And write in even more simplified form if you want. It is also equivalent to Now this is as reduced form as you want. That the probability is decreasing by this constant factor 1 minus 1 over p in every step. That's all it happens. So just give me one choice. So your choice was not wrong. Just the form is of this. So the probability that L is greater than or equal to I is simply 1 minus 1 over p to the power I divided by. So this is one choice which satisfies this. Any remarks on this distribution? What kind of distribution is it? And why is it making the cost of all deterministic algorithms the same? We're convinced that the cost of any deterministic algorithm is now same because we never chose any particular value of I. We said this is true for all I. We computed a distribution for which satisfies that purpose. So in fact, the expected cost of A1 is same, A2 is same under this distribution. What exactly is happening? Silence is not good. It's not clear. Ask me what is not clear. Something strange is happening, right? What is the expected cost of A1? Think about it. Expected cost of A1 is A1 always buys on day one. That is almost freezing something. I'm saying expected cost of A1 is same as expected cost of A2. So what is really going on with this distribution? A1 seems to be a bad algorithm. What is expected cost of A1? Oh. Now what is it telling you? That on average, every algorithm is paying P with this distribution. Right? So have I done a good job or have I done a bad job? I found a few which is bad for me or a good for me? It turns out that this objective is now easy. Because I don't have a minimization. All of them are equal to. Okay. But look at what that Q is going to do to the OPT. That's the important. What is the expected cost of my OPT? That's also a play, right? The numerator I have frozen it equal to P. So C star is always equal to P. So there is nothing happening in the numerator. What's happening in the denominator is what is interesting. And that is what is going to give me the lower bound. This quantity is what is actually going to give me lower. What I have done is I made my job simpler by computing C star. But in the process, I've not lost everything. It might appear that I've made all algorithms look equally bad, that the cost of all of them is P. Remember, what was the cost of my algorithm, which was picking the optimal deterministic algorithm? That was 2P minus 1. While the OPT got an advantage of only paying P. And that's how the ratio went to 2. Now, I'm bringing my expected cost of the algorithm down to P, and at the same time, not allowing the OPT to reduce it much further than a constant times a P. That is what is going on here. So now all we need to do is to compute just this quantity because the numerator C star is always equal to P. So I can get here. Expected value of P simply capital P and P times. Now you can guess why that 1 over E is showing up. Okay, so let me use this. So mu is larger than P divided by that quantity, which is P times plus minus. P and P cancel, and this people know as P goes to infinity, mu. I'm just taking the limit of this quantity as P goes to infinity. Otherwise, you get a value for each P or whatever fixed finite P you might have. That is what you get. And this should be increasing or decreasing as a function of P. Why am I saying I can take P going to infinity? How does it behave as a function of P? For me to claim that it's okay to look at P going to infinity, what should be the behavior of this quantity? Does it do it? This is a familiar quantity, 1 minus 1 over x to the power x. That's what quantity is. What happens to it? Leave that. Okay. So what have we achieved? That the lower bound on the competitive ratio of any randomized algorithm for the key rental problem is at least as much as 1 over 1 minus. You can't beat this by coming up with any algorithm. This gives you a universal or a fundamental bound that don't come up with an algorithm and try to prove that this is better than this because there is something wrong. And once you achieve it, your job is. So people attempting yesterday's exercise might have already seen that you can actually achieve this just by direct attack on the problem. Any questions? I see worse silence than yesterday, so I don't like it. You should be able to say something. Either it's not clear or if things are going all right, I should be able to get that sense. So say something. Point is not to run away after saying something which is not clear. So feel free to express your opinion. Just to make my job easier. My job, even after choosing a Q, was to find this quantity, which may not be a trivial job. So for each Q, there is possibly a different A. I don't know how to do that. But one possible strategy is that suppose for a Q, all the costs are the same. Then I don't have to find them. All of them are equal. No. See, this is a very special problem where you're able to index all possible deterministic algorithms by a single variable. It's never going to happen for any problem. Sorry? Can there be? In this case, can there be? And we did achieve if you were attempting yesterday's homework course. You can actually achieve this. In general, that guarantee doesn't come with this. All it says is it's a lower bound. It doesn't say how to achieve it. That's your algorithm designer's job, how to get there. So this gives you, it's essentially an information theoretic converse that you can't breach this. Now you go ahead and design your algorithm to come close to it or like it. Were you here yesterday? So if you go beyond P, the cost is always larger than this. So you can put all the mass on P if you want. There is adversary. And I'm choosing a distribution. There is always an adversary. I said this with a caution, word of caution to begin with. This lower bound is not against stochastic inputs. This lower bound is holding against all possible adversarial inputs. We created this in-between artificial object choosing a distribution over an input. All it did was to just give us this. This does not mean that we are proving guarantees against stochastic inputs. We are proving guarantees against worst case inputs. So keep that in mind. We are not producing guarantees for stochastic inputs. All we are doing is, here is a recipe to come up with a lower bound against all possible adversarial inputs using a stochastic distribution over the input. The end result is very strong. This in between route is giving you a narrow path of escape. What does it even mean? One distribution fixes an input. Once you choose a distribution, input is essentially frozen. You're just making realizations from it, and you're looking at an ensemble average of it. Yeah. Yeah, but that's you're taking an expectation with respect. So it doesn't depend on one particular realization. Any other questions? So this might look too simple for this particular problem, that suddenly I did something to choose a queue and something happened. This itself is a very highly non-trivial object, and don't underestimate its like power. It's transforming a very difficult problem into a very difficult problem. Don't think that a very difficult problem has suddenly become easy. This is in general a difficult problem. I don't understand what you're saying. Can you say it again? Yes. So this holds for every queue. Right. Correct. You could find another queue. Yes. Yes. P star is not important, right? I care about the ratio. What I care about is this ratio, how small this ratio can be. For each queue, you might get a different number. I agree. But in this particular case, for the choice I made, I got to this number. And I already know that I can achieve this number. So there is no other queue which can do better. There is no principal way of choosing queues. Let me be as frank as that. It will depend on how much you know about the problem. It's a soup. Yes. But that's a stochastic. Right. Yeah, but that's a completely stochastic problem. Right? Already why this worked out, that is, uh, people must have spent a lot of time. But it's not too unrealistic. If you actually stare at this expression, somebody guessing that I can come up with a distribution for which all of them are equal is not very high. This expression is very easy to see. That's the point for this particular problem. So that turns out that's magic. That's why would it turn out to be the right thing? That nobody could say. So that must have been the possible way in which people progress. So why that gives you the optimal thing? That converses never tell you. Each converse has its own strength. All right. So I just want to remark one thing which I missed yesterday, that I kept talking about worst case inputs. So if you at least looked at homework problem number 2 yesterday, you would have noticed something interesting. So around 3-4 years ago, what people said, okay, this is worst case is too bad. The algorithm's performance can be improved by knowing something about the input, which my strong machine learning algorithm can predict. So suppose you have a machine learning algorithm which can predict the input. In this case, somehow it's collecting data from all over the world about mountains and things look like at least up to some error. Now, if you have this additional prediction about L, so let's call this L hat, okay? And let's call the error to be summit. The problem is that I don't know it. I have an estimator for L, which I represent as L hat, and there is some error between the true value of L and L hat. Can you come up with an algorithm? This is very interesting program. With a single online algorithm. Whose competitive ratio goes to 1 if eta is near 0 without knowing what eta is. Okay. If eta turns out to be good, your competitive ratio should go to 1. If eta was 0, I'm in essentially offline mode and I can always get competitive ratio 1. What I don't know is what eta is. So in one regime, that if eta turns out to be good, without knowing it, my competitive ratio should go to 1. Otherwise, my competitive ratio should be bounded. It could be a function of eta, otherwise. So this is the new regime which has been suddenly gaining interest for the last 4 or 5 years, which is bridging the gap between stochastic inputs and the worst case input. If you think about it, this is a very imposing task for an online algorithm. Without knowing what the error is, it has to come up with a single online algorithm which is close to the OPT if the error is very small and it is bounded competitive ratio no matter what it is. There is no algorithm. L hat is somebody else is giving you L hat whose accuracy you don't know. That's you can think of it. Your friend is telling you L hat is the estimate for L, but you don't know how much to trust that one. Now, without knowing that trust value, you have to come up with an algorithm which can do these two jobs simultaneously. That's the difficulty. If you solve the problem number 2, there is one such algorithm for ski rental problem. It's very simple. If you've not seen it yet, please go back and see. It's a very simple algorithm which can achieve both these objectives. And this new regime is called Beyond the Worst Case is actually becoming very popular for almost all online problems. And many of them remain open. All right. People appreciate the difficulty here, right? What the difficulty in online algorithm. What we have here so far is the second point. That no matter what the input is, how it is generated, I will have a bounded competitive rate or a small enough competitive rate. Now I'm asking that if the prediction turns out to be good, the competitive should necessarily go to 1. That's a very hard extra constraint I'm imposing. And again, the point is that you can do this. So this bridges the worst case people and the stochastic people in a very nice way. If you are not a worst case person, you should only look at this kind of thing. That suppose I have a predictor, whose accuracy I don't know, I should be able to come up with an algorithm which can do the fit all size job at the same time. All right, so I'm going to switch problems today. This is all there is for the ski rental. You simply characterize both the deterministic as well as the randomized sets. Yes. If the predict if no if eta goes to 0, the competitor so whatever competitor no you don't know L. This is some sense just telling you how small the error is. Because it's a problem because it's integral. Just think of it doesn't. So what algorithm I have prescribed, it doesn't go anywhere. It's a completely different algorithm. No. A small tweak. So you have to tweak it. You can't use your own algorithm and expect that this will happen automatically. You will have to use this extra information in a very clever way so that you remain bounded if eta is bad, but you get very close to OPT if eta is very good. That's the enormous power I'm asking you for your algorithm to have. And it's not easy to. In ski rental case, it turns out to be both the algorithm is easy as well as the analysis is easy. So that's problem number 2. So I chose that problem with very specific reason, which illustrates that you can actually do this. Any other questions on fee rental before I move to the next problem? So I give a primer for this. Now in more detail. So let there be infinite supply of bins, each with capacity. So you have this. You don't have any constraint on how many bins you can use. Input item with size, with WI arrive frequency. So all here is the online restriction on arrival of item I. Uh, it has to be assigned to either a currently used bin where it can fit. So by fit I mean wherever it does not exceed the capacity of the bin. So currently each of the bins at this point have certain items which are assigned to them. A new item is defined to be fitting in that bin if the sum of those weights do not exceed capacity. That's what an item can fit a particular bin. Or true, open a new bin not being used currently and assign it. So far so good. You're not allowed to change. What this tells you is that you're not allowed to change the configuration of previously assigned item. All you can do is the new item can go in any of the bins where it can fit or to a new bin. That's the restriction. That once the input ends, let the number of bins used by any online algorithm be B sub A and and I define mu A to be max over my input BA over, and my job is to come up with an algorithm which has small mu or the smallest bin. No, we don't know that. So this, so you should also keep this in mind that these guarantees I am giving you is for any input. So it could be input of length 1, 2, 3, 4, whatever. In very special or special cases, you need to know the length of the input. In this case, we don't need. So you can terminate your input anytime and the same guarantee will hold. That's ingrained into this definition. Because I'm looking at max of sigma. That sigma, which terminates at whatever time you want to terminate, is included in the maximization. We didn't look at expected competitive. That's a different quantity altogether. You can take the competitive ratio and take the expectation of it. That's completely different. What we have done is we looked at a randomized algorithm whose cost is expected value of something, but the denominator still remains for a fixed input. All right, so exercise, can you come up with an input? Not very difficult. for which mu A is greater than equal to 4 by 3 for any A. When people think about it, it's not difficult. If you understand the problem definition, this is not very difficult. What am I asking? That produce an input. Now input doesn't mean a single parameter. Now input means weight, item number one's weight, item number two's weight, item number three's weight. You're allowed to choose whatever you want. One, capacity is one. And so all WIs are also between 0 and 1 without loss of generality. No, up could use 6 bins and you could use 8 bins. It's a ratio. So it's not necessary that op should use it. All I'm saying is the ratio is perfect. So you have to somehow make sure that any online algorithm, because of its myopic view, is going to need at least 4 by 3 times OPT. So this should be, this is not very tight at all. Just to make sure that we understand what we are doing. So what could be an input where OPT has an advantage over here? How should these WIs come? OPT knows everything ahead of time. You know only the current value. What assignment you can make a mistake. That is also true. So now you have to give an input such that that penalizes you. Okay. Correct. But why would you need that? That will define your next input. That is under control for you. You are an adversary. You can control how this input is revealed. The saying is the right direction that knowing few number of items initially, you would try to do some packing. And that packing should not be the optimal packing for the input I can reveal next. So just such one such example. I am okay with anything more than one, not necessarily 4 by 3. So you can have, so suppose bin number 1, bin number 2, so on. Some items will arrive sequentially. Because of your assignment and the limited view, you will make certain assignments. Think of an input which will make sure that that assignment you made until so much time was actually not the optimal assignment. Going back, no. Going forward, yes. Very good. So what? So suppose the first 3 items which arrive are of weight 1 by 3, 1 by 3, 1. What should an algorithm do? Tell me first. Any reasonable? We are asking for any So when I say A for the moment, deterministic algorithm. What should any reasonable algorithm do? Slightly louder. Correct. Because if it doesn't do it, then what should you do? Suppose it doesn't do it. Can you give me a bound which is even better than 4 by 3? Right. So it's already 2. If any algorithm does not put all these 3 bins, all these 3 items in single bin, then I can just stop the input right there and make sure that the competitor ratio goes to 2. So OPT will definitely put it in 1. Right. So that's a good start. Now suppose all 3 items are sitting here. Now depending on this allocation, find a new input. What's the next input? Very good. So now where these 2 by 3 have to go? Necessarily in new one, necessarily in new one, and necessarily in new one. Because I don't have enough space to accommodate any of these 2 by 3. Now, if I knew this is my total configuration, what would OPT do? Just pack these 2 items together, these 2 items together, and these 2 items. Using only 3 bins, while your algorithm needed 4. This is true for any deterministic algorithm. Very good. So now we need to do something on trivia. 4 by 3 is already there. So this is a lower bound, mind you. I'm not giving you an algorithm which can achieve that. because I can always produce an input for which the algorithm you are going to prescribe might not achieve 4 by 3. Now let's try to construct an example of an algorithm which always does a competitive ratio of 2. Can somebody think about it? That's also easy, I claim. Here is the lower bound for 4 by 3. Now I'm asking for an upper bound of 2. Greedy. Okay, what is greedy? Define greedy for me. That is already the space remaining after the input or before? Or does it matter? No, no, you fine. Just tell me one choice. Whatever choice you make, that will be an algorithm. Least, right? Not most. Most is a bad idea. Then you are actually, you go to any bin. Right. So, but there are 10 open bins. What do I do? So let me just make it concrete. So suppose at this point of time, so bin number 1 has level L1, bin number 2 has level L2. So level is the sum of the weights of items already assigned at time I when the item I arrives, and so on. And that is the this is your configuration. A new item WI has arrived. Now tell me where should I put it? First of all, it should fit, otherwise that bin is out of the picture. So only consider the bins where WI can fit. Right. Okay. No, I'm not able to understand. So I'm only writing these where WI can fit. So that is given to you. So all these L1 to Lk are such that Li plus Wi is less than or equal to 1. So that is, otherwise I don't have to look at that bin which can't even accommodate Wi. After or before? Okay. So you can just simply say largest L1. So that's one choice. So pick bin A largest. And again, just to belabor the point, I'm only considering bins where Wi can even fit. Otherwise, I don't have to worry about it. So this actually has a name called best fit. It's trying to minimize the wastage. Equivalently, you can think of this problem as trying to minimize the wastage at the end of the input. And wastage will be the leftover capacity in each of the bins. If you could break the item, you would completely pack each item, each bin. Just because you can't break these items into smaller weights, you will have eventually some unused capacity here, some unused capacity here, and so on and so forth. All we are trying to minimize is the sum of the unused capacity. You can think of it in that way as well. So that at the end of the input, all I count is for each bin, how much is the unused capacity, sum it across that. That's an alternate metric of formulating this problem. Right? I never said this is the only algorithm. All I'm asking for the moment is any algorithm which is a competitive ratio at most of 2. That's all I'm asking. There are many different algorithms you can come up with. All of them reasonable, meaningful, having a good guarantee. This just has a name, so I said called best fit. If you just tweak this, it's called first fit. So find the earliest opened bin where Wi. That's called first fit. Is the algorithm definition clear? That there is a time index at which any particular bin opens up. So I look at WI and look at all the bins where it can fit. Pick the bin which was opened the earliest in time and just assign that item. So it's called first fit. What she suggested was best fit. You can come up with your own understanding of any fit. All you need to show me that any of these have a competitive ratio less than 2. Yeah. Huge difference, right? Right? That, yeah, right. No, no, you're doing this in ordered manner. Are you saying best fit, the configuration which best fit will produce is the same as the configuration that first fit will produce? It's not. So you can come up with an example on your own. What is the process you're suggesting is correct. You're doing it sequentially. But so you fixed one algorithm, right? So every time a new item arrives, I do this either using first fit or best fit. You can easily construct an example where they don't match after a while. But both of them have a commonality. Both of them have a competitive ratio at most 2, trivially. So can somebody give me an argument? Who is not what we are shooting for? We're just beginning with 2. That's not too bad. The adversary doesn't have too much power. Yes. What is nothing doesn't have? Can you make this more precise? That's not entirely true. Just need an extra caveat. Right. So that's the observation you need to make. That with any of these algorithms, there is at most one bin which has weight less than equal to half at any point of time. At time, there is at most one bin, or if it's open, one open bin with level. Okay, so why should this imply a competitive? This is enough to imply a competitive ratio of 2. Do people agree to this property first of all? Can there be 2 bins with weight less than half? Just do the contradiction. So suppose there are 2 bins with weight less than half. Something is going wrong with the algorithm. What is that which is going wrong? Because that was available and you didn't use it. So you're not following the algorithm. So it cannot be that you have 2 bins with levels less than half at the same time. Is this clear? So suppose there are 2 bins, B1 and B2, with level L1 and L2, and both L1 is less than half and L2 is less than half. Can this even happen with any of these algorithms? Because suppose this was opened before. So whenever you did open this bin, there was capacity to assign all these items here. But without loss of generality, let B1 be opened before B2. So all the items which are getting assigned to B2 could have been assigned to B1 because there is more than half space available and you're only occupying less than half here. So you're not conforming to any of these algorithms. So by contradiction, it can only be that at most one bin has a level less than equal to half. So why does that imply a competitive ratio? Yes. Can you make it more clear? Right. The number of bins used. Correct. At least that much. Even if you were to break item, you will at least need one. So divided by mu of best fit or mu of first group from my property. What can I say? The number of bins used. I'll do it for anyone. Let's call BF. By BF. E. What is the total weight or the sum of the weight of all items assigned so far in terms of BBF? At any point of time, my best fit algorithm is using B sub BF number of bins. So can you lower bound the sum of the weight of all the items assigned so far? This is at least BBF minus 1 by 2 from my property. Except the last one, I don't know how small that is. Everybody else is at least 1/2 the weight. So at least the sum of the weights of all items assigned so far is so much. The OPT also has to pack up so much weight because these many items have arrived. OPT also has to do this job. In the best case, OPT could even break these items and pack them perfectly without wasting any space in any of its bins. But even then, it at least has to use this much, these many number of bins. So BOPT is greater than this quantity. And what is my ratio? It is BBF divided by BOPT. So I get 2 for free. Now I have to work hard to get something better. And let's stop at that point. We'll continue in 10 minutes and show that we can actually go to 1.7. That's a non-trivial analysis. Yes? Yes? That's a bad algorithm. Greater than half I can understand. Okay? No. So what is your algorithm? New bin. Then it's very bad, right? Your competitive ratio is 3 actually, not even 2. So think of their input where these guys don't even arrive. So that's a bad algorithm. An algorithm which chooses to put heavy items individually, heavy meaning weight one more than 1/2, that's not a bad algorithm. But the smaller the items there are, smaller weight items, they should be packed efficiently. 1/2 items are not very important. We'll see that also in the analysis of a more finer analysis of best fit, that items with weight greater than 1/2 don't trouble us much. So items of weight small and smaller and smaller and smaller, those are the ones you have to be very careful about. All right, let's stop.
Mic check. Mic check. Check, check, check. Check, check, check. Check, 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 check. Check. Audio check.
So any questions before I do some non-trivial analysis of best fit? And please ask questions. Don't worry about what that question might be. If you lost anything, this might be a good time to ask me. Because now I'm going to do some fun analysis of best fit. So if we get any conceptual question, even about skill rank, this is the time to ask me. Pause for a few minutes. Hoping for a question. Yeah, I thought so. Anything about conceptual, house recipe, competitive ratio, definition of an online algorithm. It could be any. Don't hesitate to ask. No question is troubling. Don't ask why we are doing. That's the only question you should not ask. Everything else. Okay, so what did we say here? Forget it. What did we say here? Like the sum of the weight of all items. That is so. OPT also has to assign to that. You cannot go for the total weight of items to be assigned down is at least that. Each bin has a capacity one. So how many bins should we make? If the total weight is 10, each bin's capacity is 1. How many bins should we make? At least. How many? Whatever the configuration of this bin might be. Some of the weights is 10. In each bin, I can put only weight of total weight on. How many bins? At least 10. So the number of bins used by OPT is at least the sum weight on the item seen so far. There's no other. Nothing. You take examples. Some weight is at least 10. How many bins do you need? There's no difference. First field, then how would we say that it is up or down? That was each two. So that's Like we do for bench weight press, we can do the same thing for speed. In that one, we didn't say everything. And we can talk with your situation. Right. And is it true for worst fit? What is worst? The largest, I'm going to bed for example. That's the very, but we can come up with input. Just to not make sure that it is important. So whenever you're thinking of an algorithm being good enough, always think of an input which is respected. First, here is my input, which will never allow me to be too complicated. If you can't come up with after a while, then you should think about moving the that it is. Always begin with start. Think of an algorithm, it makes sense. Always think of bad input. That should be the first exercise you do. And once you're convinced that the bad input is not too bad, then you should try to you have to do anything for it. So it is probably absolutely clear to everybody what the impact problem is. Something should be clear, and what we are trying to do should be clear. If you lose somewhere in the middle some step, that I don't mind. But don't lose conceptually. Then it's my problem. I don't want to bring any. In your notes, you find all sorts of precise notation as well as precise definitions. Here I'm not doing that. I'm not going to say asymptotic, non-asymptotic. But there is distinct classification in your notes. Keep that. You'll understand what. No more questions? Now to go ahead. Everybody give me permission to go ahead. I'm happy to stop and take questions, make any clarification. Oh, so this is clear. That's what I want. We already seen. You already know a lower bound of 4 by 3 for any algorithm. So this is something in between. Without definition. Then, where currently defining a level of a bill depending on what he sees for the side. Not after the cycle, this is before it. On the level of item. And level is being level is the sum of the weight of all the items and paid for it. Define level just before the level of item I. I'm defining the level of item I as the level of that thing. Then I will actually get a assign the level of goes to. So how much should this number be? Let me even try to do the following. So during the execution of the best fit algorithm, I'm saying consider any two open bins and sum their levels. What should be a number? Get two answers. Two is trivial because 1 plus 1 is capacity is 1. You have to say something not true. But it's not. One. Very good. So cannot be can it be equal? Greater than. If you don't see the proof, I'll come back to you. For the moment, we will go straight to it and goodbye. Was not. Sir, so suppose an item A arrives and gets assigned to a particular bin, whose level just before the arrival of A was at most 1. That's what the definition of level is. When A is arriving, the level of the bin to which it is assigned is by definition the sum of the weights of the items assigned to it just before A arrives. What are we doing? Suppose an item A is going to get assigned to a bin whose level was 1/2 on its arrival. Then the claim is that there are no other open bin where A could have fit.
It does fit to
Sorry.
if it does fit to that,
Yes.
it will.
So again, contradiction. Just stating this result right now, proof will come. But the claim should be true. Claim should be clear. Claim is that if I'm assigning an item to a bin whose level is at most 1/2 when I'm doing this, there is no other bin where this item is. Third property. Properties are essentially elementary, but will come to our help in a very meaningful way. If there are bins, B by. So both level is at most 2. And B was open before B prime. Then after B prime contains a single item or the first item that was assigned to B prime of weight greater than equal to. Again, it's a statement here. Suppose there are 2 bins. Consider you say level is at most 2 by 2. Both these levels are at most 2. And B is open before B. So that takes them time out. Then either B prime contains a single item. So either there is a single item sitting in this. Or the first item which went into B prime had a weight greater than 1/2. If you're not convinced, we'll prove it. But it's very easy to see if you essentially put these things together. So one and 2 and some thought in it. Yes. Yes. If I am assigning it to that, if I am, so this is an overload of definition. Asking you which bin you are assigning to, look at that level. Level is defined just before the arrival of this item. That's a independent definition. This is overloaded. Okay, so now comes the real punchline. What are we trying to do? So let me sketch out what we are trying to do. What is best fit trying to do? That it's trying to minimize the wastage you are going to commit in each of these bins by making sure that every time there is space in a bin, I will not open a new bin and try and go and minimize the wastage. That's the broad idea of this. Now, how do I come? So, supposing I'm also going to call an item of weight more than half as a heavy item. There will be light items, there will be medium items, there will be heavy items. Heavy items are the easy items to handle. For heavy items, I will not worry about how best fit is packing them. I'll just look at all the bins where any heavy item is put, just keep on the side. I'm not going to worry too much about it. We count as it is. I worry about all the bins where there are no heavy items. Those are the ones I have to worry about. And try to combine 2 consecutive bins in some way. That if weight of one bin is not too large, then the weight of the second bin. That's the broad idea of this. That suppose I'm unable to pack up one bin completely before I'm moving on to the next one. There is some correlation between consecutively open bins with the best one. If I don't incorporate that, I'll get a competitive ratio of 2. All the improvement I'm going to get from 2 to 1.7 is because of the fact I'll be able to combine what's happening to 2 consecutive bins. And consecutive is not absolute consecutive. I'll drop all the bins which contain any heavy items. So when you look at bins which do not contain any heavy item, then try to combine what's happening across 2 consecutive items. Because that's what best fit is trying to do. That if is unable to occupy the complete weight of one particular bin, we'll try to increase the occupied weight of the second. That's what we'll try to do. And this is a generic idea of amortizing the cost. If you are coming up with an algorithm which cannot do at each step good things, you should be able to say that if I am unable to do good things at step 1, I should be at least be able to say something across 2 consecutive steps or 3 consecutive. My algorithm is efficient enough to allow me to not do the greatest thing I want to do at each step, but at least across steps, if I can count, I can amortize the cost better. That's the broad idea of this. I will try to combine what is happening across two consecutively contains which do not contain any free items. So this is, it might look very narrow idea, but actually it's useful in many different ways. Where you're making local decisions, but they're not very local. Like Westwood is not very local in some sense. It's actually trying to look at in the past, what have you done with your allocation and trying to pick one bill which has the least amount of room available. That's what the algorithm is. Towards that end, we try to define new pointers. Value function. Don't mistake it. Value point. What is it called? Indra, what is it called? Value function in policy at least in English. This is not that. This is some other value function I'm defining for each item. For each item, we define VI bar and a VI double bar. This will be 0. Bit of the item is less than 1/6. By 5. 6. This is the first step in trying to amortize the cost across two consecutive open days. Sorry? 6.4. For heavy, so these are the heavy items for which the value VI bar is just 0.4. You think of this as some kind of quantization going on. If you're above half, I'm always going to count 0.4. I don't really go beyond that. So between this is 0.4. This is the only one which is not quantized. It's changing with respect to W. And these are quantized down, these are quantized. Everything is actually getting pushed down. Another quantity, which is VI double bar for each item, which is simply 6 by 5 times the weight of. And this is inflating it. It's 1.2 times the weight. Which is smaller than the weight. Definition clear? For each item, I'm defining this quantity. Just define. How to define? That's my prerogative. How I use this, then you can put. Just for the moment, it's just a pure definition depending on the weight of the item. Nothing to do with the algorithm, nothing to do with what I said. Use this for amortization. So for some item, I will try to combine the VI bar, and for some item, I will try to combine VI double bar. That's what is going across. That's what we. Hopefully that should be clear. Why I've done. Think of this. This is inflating the weight, and this is deflating the weight. And final value VI is nothing. VI. First. Yeah. Now you see why I do this. This is algorithm independent level. Nothing to do with the algorithm. For any subset of items. That's done. Look at any subset whose sum weight is less than equal to 1. Let the V of S, which is nothing but summation of I belongs to S. see the proof? This has nothing to do with the algorithm. I'm just defining some quantities, Vi and Vi double bars, and I'm saying, look at any subset whose sum weight is less than or equal to 1. The inflation factor is no more than 1.7. That's all there is. Summation Wi is less than 1, the summation Vi is less than 1.7. So whatever I defined there, I'm not inflating it more than 1.7 times. It requires proof. It's not an immediate factor. But I'll keep that much one side. Otherwise, it will impede the flow. But this is acceptable. Something like this should happen. What correct number is, that's okay. But if you see from there, something of this sort should appear. 1.7 is not obvious. You could guess really that 1.2 is already there. The extra 0.5 is all I have to account for. There's not any more than 1.7. That's the 0.5 is the non-trivial part. 1.2 is for free. And this has nothing to do with the algorithm. This is pure definition. Now use this lemma and tell me something about what will OPT's cost in terms of its value. So sigma is my would be right script R, a set of items presented in the input. Because offline acts on the full I directly. What is V of I in terms of the number of bins OPT will use? Can somebody say that using that time?
1.7 times
0.7 times how much?
DOT.
That's correct. So this is at most. This I am showing one. You should be able to see it. Anybody who doesn't see it want to work on it? Why this should be true? Directly follow it. What is the constant OPT works under? It can also not pack items of some weight more than one in any bin. So any bin it uses, the total amount of weight assigned to that bin is at most 1. Just following that and lemma should imply this. You can write it. So what is V of I by definition? Let's say set OI is the set assigned by OPT to bin I. This is okay. This to this equality is true. OI is the set of items assigned by OPT to bin I, bin BI. And what should OI satisfy? OI should satisfy that summation of WI for I belong to OI should be less than or equal to 1. Think of any bin I used by OPT. What is the sum of the weight of items sitting here? At most 1. So if I replace S by call it OJ, so summation I belongs to OJ WI should be less than 1 for OPT. That's all. Because of the lemma, this is at most. The sum remains as it is. So this is the real reason, first real reason why I want to do this. That this quantity is an absolute quantity. This has nothing to do with the algorithm. Think about it. This is defined for the set of items and its valuation. It does not depend on what algorithm we use. And I'm still able to connect this with the number of bins OPT is going to use by this extra factor. If you want to guess the proof of this, what do I need to show? Once I have done this, the number of bins used by OPT and the value I have connected. Show the proof or complete the proof. What do I need to do for an algorithm?
Number of bins opened by best fit is less than 1.
That would suffice. If I could connect this and the number of bins opened by the best fit without any inflation factor. So now I've already got 1.7 as it is here. So now I can't have anything more because otherwise the competitive ratio will go up. Somehow I have to convince you that this somehow is connected to the number of bins opened by OPT without any multiplicative factor. An additive factor will be fine. That is what we will do. Are we good here? This is the, more or less the outline of the proof.
By additive factor is fine.
The competitive ratio is a fraction of so even if I can bound something as an additive constant there, it should not. But don't worry about it. Are you good with the plan? More or less? What are we trying to attempt?
So when you explain that, Parallel function is more or less with what algorithms are. Comparing a Parallel relation given that time.
Why? Because of this constraint, even the OPT has, that the sum of the weight of the items put in any bin has to satisfy this. So I'm using this lemma, which I have not proved yet, to connect the number of bins used by the OPT and the value over the full input sequence. That's the handle I'm able to create just by exploiting one constraint which OPT has to satisfy. That's all. The value function is an independent quantity on this. This is the first purpose value function serves. The second will be to combine across bins for best fit. That's the more important. For the bins which do not contain any heavy items. Okay. So we'll write one more lemma without proof and then I'll prove and then I'll come back to it. Then this. Doesn't bother anyone too much, right? That I'm writing these lemmas without proof for the moment. Because if I get bogged down for proving this, the flow will be broken as the only object. Okay, so final lemma. Let's name that. Fine. From there. This is the hypothesis. Yeah. In such W K has a size more than 1 minus WS. That is, it cannot fit in the same bin where S is. And WL. Then, this is the punch line of what we do. V double bar of S. K single bar. VL single bar. So at least that. So this is the second purpose of defining these value functions V bars and V double bars. What we say? Think of a bin where a set of items S is assigned and the level at that point is greater than 2 by 3. That's all this is.
And does this be a dependent?
No, this is an independent lemma. We're not doing anything. Suppose this is true. Suppose a bin contains a set of items S whose sum of some weight is greater than 2/3. And let there be two other items which cannot fit inside because of the capacity. Then this relationship has to be broken. So my definition of V bars and V double bars. So more importantly, you should see that this is a V double bar while this is V single bar. So this is the amortization step. This is how we'll actually use this. So there's one set which cannot accommodate VK and VL. we are going essentially to the next bin. I will be able to combine the weights across these two bins using 1 bar and a two bar across these cells. That is what is going on. If you are unable to, so think of this as you are following a best fit algorithm and you are unable to fit this VKs and VS. Wherever these two go, there is some relationship between the value assigned across these two bins. If I'm unable to do this, the best ratio I can get is 2. It's because of this fact, the 2 can be pulled to one class or to anything less than 2. Let me call this the amortization step. That I need to amortize the cost across different periods.
Functions maps from rate of the item to a value. And the V of S will be different.
Yes.
That
V of S is just a summation of the set below. Okay, so now the proof for the thing. So heavy items, remember, are weight items with weight greater than half. A heavy bin is a bin that contains a heavy item. See, 2 heavy items cannot be in the same bin, so it's exactly 1. So what is the value of a heavy bin? Let's say HI is a heavy bin. What is V of HR? At least, in my definition. Correct? V of HI, not V bar or double bar. Very good. Do everybody see this? Why is it greater than? Just by definition. So pick the element which is heavy in there. This will give you how much? 1.2 times 0.5 at least. That will give you 0.6. The rest of it comes from where? 0.4. Because WI is strictly greater than half. 0.6 plus 0.4 is at least. So these bins, will keep them aside. All the bins which contain heavy items are all heavy bins. We will only worry about this point. Do not try to amortize anything. Now we will use proposition 1 to imply that there exists at most one bin with level at most. Call this bin E1. You also not touch E1. Proposition tells me this. There is at most one bin whose level is at most 1 at any point. Just call that bin E1. Just name them. Keep it aside. I'm keeping aside heavy bins. I'm keeping aside E1. I'm going to keep aside one more. This also tells me that there is at most one bin with 2 or more items such that the level of the 2/3 are convinced more. Call this bin E2. So both of these facts are coming from my proposition one, which I have not proved yet. Now we are back in business. So we'll keep HIs aside, we'll keep E1 aside, and E2 aside. And now worry about all other bins which best fit is going to fit. And for that, this property will be produced. Plan clear? I'm not going to touch. See this one of it, right? So I don't have to worry too much. This is also one of it. I don't have to worry. These guys already are containing at least one heavy item, so they're occupied with more than half the weight. So the wastage is only half. So I don't have to worry too much. It's the rest of the bins I have to worry. That what is exactly. So let me write this. Alright, so let's name B1, B2, all other bins used by BF other than HIs, E1 and E2. Okay? Definition clear? Heavy bins kept aside, E1 kept aside, E2 kept aside. Remaining is what? I'm going to do it. So what is that we know about these bins? They have levels more than 2/3 and contain no. This by definition, because everything else has been kept in H's and even in H's. Now consider, I want to use this lemma. This part is already true for all these bins B1 through B2 by default. That the weight of these items, some weight of items in any of these bins is at least 2/3. Now I'll create and see two items which cannot fit and what happens. Consider two items, K and L. That are BI plus 1. Why? How do I guarantee that there are two such items? 2/3 and each of them is less than half. So there better be at least two items in each of these bins. You okay? Level is greater than 2/3. That is, sum of the weights is greater than 2/3, and each item inside is less than 1/2. So there will at least be two items in each of these bins.
Here, are you talking about a bin?
Sorry?
I didn't understand. This context I didn't understand.
So by definition, all these bins B1 through Bn have levels greater than 2/3 and contain no heavy items.
Are we using this lemma through?
Yet to use them.
Because you're ensuring that it is, you're saying that all these bins have weight more than 2/2.
Yes.
And no heavy item.
Yes.
So are we defining like that those bins?
Yes, because everything else has been kept aside. HIs are all bins which contain a heavy item.
Yes.
And from my proposition 1 and 2, there are at most two other bins which do not satisfy this property. So every other bin satisfies this property. All those are called B1 through Bn. This is just by definition. Now the fact that the level is more than 2/3, contain no heavy item, implies that there are two items in each of these bins. I'm looking at any Bi plus 1. I want to go back, connect it to Bi. Let these two items, K and L, with individual weights less than half, be assigned to bi plus 1. I want to say what happened between bi and bi plus 1. And indexed in order of opening. B1 through BM are indexed in order in which they were open. So B1 was opened before B2. There is no prime. Okay, so BI plus 1 was open after.
I'm not getting this. It's like an E2 which you got. I'm guessing you get in proposition 1, 3, but I'm not seeing that.
No, no. Just let's read that. There are two bits B and B prime, which level at most 2/3, and B was opened before B prime. This much is okay. Then either B prime contains a single item, or the first item that was assigned to B prime was of weight greater than half. So either it became heavy, or it contains a single item. So how many bins can actually have single items with at level at most 2/3? Just by contradiction of this. So can we come back?
Sure.
This is true. Yeah, it's actually true. It's not wrong.
No, no, I was not able to derive
Yeah, that could happen, but it's not making sense.
Actually, definition of equal. Sorry, at most be 2/3 or at least 2/3.
So that level of at most, they want all these guys to have level more than 2/3. What I want to make sure that if there is a bin with level at most 2/3 and contain no heavy item, is at most one of them. So I want to make sure that there are not too many of these guys, for which I am not going to touch. There was I. Valid question, you come back. If there is time. Otherwise, there is a. So we are close to the door. So VI plus 1 was opened after plus A. First time. That's a constant. K be the first time. K. Assigned to BI. BI plus 1. Could not fit in BI. By the definition of the algorithm, I'm assigning the first item. So let K be the first two items. First two items that are assigned to bin BI plus 1. The fact is, BI was opened before BI plus 1, and the first item, which was assigned to BI plus 1, could not have fit into BI because otherwise K would have gone to BI by my algorithm. The fact that I'm going to the next one ensures that I could not have fit into BI. Apart from this, this. Hopefully, Two bins B and B prime. B was opened before B prime. It doesn't have to be consecutive. Just that B was opened before. Just before. How much this should be? It be greater than 1 minus WK by the very fact that it cannot fit. And WK is less than half by definition. Where WK is there is by definition. Thus, given that L, the second item, L, second item, sign one. See, second item. So the first item's weight is at most 1/2. So the level of this bin Bi plus 1, when the second item arrived, is simply W2. So K and L are the first two items assigned to bin Bi plus 1. So when L arrived, K is the only item assigned to bin. So if level is equal to WK, which is at most half. Now, the second property is 1 second. That's nice that L should not fit. What is the question?
Yes. Yeah, you mentioned the categories. So you're saying that the L is also assigned to BI class.
By definition, K and L are the first two items assigned to Bi plus 1. When L arrives, its level is essentially WK. And WK is at most half. So if I apply the second property, I already know that because the fact that I'm assigning L to this bin, there could have been no other bin where it could have fit. And in particular, it could not have fit in bin Bi.
This is also satisfying that greater than 1 minus WL. The level of BI is also satisfying that
Yes, but that is not okay. I already know that it could not have, so I'm able to conclude it with respect to. Moreover, by definition, rate of bin Bi is greater than 2/3. By definition. Now I apply this line. I know A doesn't fit into this bin, L doesn't fit into this bin, and the weight of S is greater than 2/3. So I'm good to apply this line. Over these two items, K and L, which are the first two items assigned to bin Bi plus 1.
Just check that K and have two items in the air custom, not that.
First, it's very important. I added K.
Oh,
It's important. First two. Now I can actually, so this was an independent level. Now from my algorithm, I'm going to extract a subset S, which is nothing but bin Bi, whose weight is greater than 2/3, and two items which cannot fit into this, satisfying this constraint. So this is true.
at the time that K and L was
They arrive.
came in, at the time K and L came in, it may not have been true that bin BI had less than weight value, but eventually it did. Therefore, that's
The K and L could not fit even with whatever level there was. So it's definitely true. The level only goes up. Level can never go down. It's a monotonic increasing function. All right. So what I can say using this lemma now is that V double bar of bin bi plus v bar of bi plus 1 is greater than equal to v double bar of bi plus v bar of k plus v bar of. This is trivial, right? K and L are the two elements sitting inside vi plus 1. This quantity is at least as much as the valuation of these two quantities. And now using the lemma, this is a trivial state. The first term is as it is. The second term, I'm only counting the two items assigned to vi plus 2. Now I'm applying the lemma to get this to be greater than. So essentially done. And I have no time to do the lemmas. What can I erase? I don't need to use this lemma. Now I'm back to total valuation over the full.
The first thing is equality, right?
Sorry. First is inequality. Strict inequality actually. If you
It's equal, right? I mean,
what? It could be more than two items.
just the first two are P and L, right? You're saying that's not.
Third, fourth.
There are others also.
Could be. I'm not counting this. V of I is nothing but I going from 1 through m. So these are 1 through m. V of I plus all the heavy bills. V of HR. Set of heavy bills. Plus V of E1 plus V of E2 is equal, right? All these I sit in some sets, some bins. I'm just writing it as a partition. Everything is additive. All these V's are additive. So this is true. See, I is set of items presented. The input. My algorithm is kept V1, V2, Vm, H1, Q, let's say H, models, P1 and P2. So all these I's have been assigned somewhere. This is essentially a partition of these set of items. And because these are additive, I can just write V of I as addition over these bits set. Now I want to not touch these guys, only want to touch this and count across two bits. By definition of V, I can write V as V bar of Vi plus V double bar of V plus the rest of these guys. I'll take first guy out of V1 plus V bar of Vi. Single bar of Vi. I'm going from 1 through minus 1 plus V bar plus everything else. I'm just rewriting in a form where I can now use this relationship. So the first term here is as it is. The last term, the double bar is as it is. Rest of them, I'm going to combine. See, one term from here, one term from here can be combined across Vi and Vi plus 1. That is what I'm finding. So V double bar of Vi, V bar of Vi plus 1. This is another way of writing this. How much do I know this is? At least. This is at least greater than 1. So this is greater than equal to m minus 1 plus V bar of V1, V double bar of Vm plus summation V of Hi's plus V of P1 and V of V. I just erased. What was V of Hi for a heavy set? At least 1. So I can also count those. This is greater than m minus 1 plus the number of heavy bits plus these 4 terms. V bar of V1, V double bar of V1, V of V1. This is nothing but V of. So what is the total number of bins used by my algorithm? M plus the number of heavy bins plus 2 more bins. Look at these are the total number of bins used by my algorithm. What is this quantity in terms of the number of bins used by best fit? How many bins am I using? M plus the number of heavy bins plus 2 more. How much am I going to count here? M minus 1 plus the number of heavy bins plus few other fringe things. So can I say that this is greater than equal to the number of bins used by minus 3? What is it? M plus the number of heavy bins plus 2 more. That's the total number of bins I'm using. Here, what am I going to count? M plus the number of heavy bins plus these positive quantities minus a 1. Okay with me? So total number of bins used by is N that's H plus 2. What have I got here? M plus mod H minus 1 plus these positive quantities. You can convince yourself this is at most number of VF minus 3. I will leave that as an exercise. And what was my V of I in terms of OPT, if somebody remembers?
Points.
Right. So for OPT, V of I, something 1.7 times greater than less than. This was whatever got there. Wouldn't work, right? If it was greater than. So this was. So we combine this 1, 2. Okay. See, VI is common. Essentially sure. That's an option. So up to this minus 3 term, this is competitive ratio is 1.7. So if BOPT was large, that will wash away. The competitive ratio will remain 1.7. This is the best result we can get from this. So the competitive ratio, as long as the number of bins used by OPT is large enough, is 1. And this is tight. You cannot do anything better than that for best fit. All right, so we're out of time. All the notes you have, all the propositions which I did not do, all the notes are there. It would be a good exercise to actually program it. Any questions on what we did? It's okay. Some parts may not be clear. Big picture. This is what big picture is. But what we wanted to do was that if best fit is not doing the greatest of job in one particular bin, next bin opened and the items some. That is why the value from this is a generic idea. It's not very specific with this particular problem. If you want to amortize cost, do something like this. You break up the actual cost you're paying into parts and make sure that those 2 parts are somehow possible to be connected across the algorithm. It could be 2 steps. In this case, it was 2 steps. I just could say VI bar and a VI double bar and amortize the cost across a bar and a double bar. It could be that your algorithm might need 3 steps depending on the choice of your algorithm. But this is a generic idea for amortize. If you keep counting each bin separately, you will not be able to get anything better than 1/2 competitive ratio of 2 because it could be arbitrarily close to 1/2. Your occupation of a bin could be arbitrarily close to 1/2, while OPT could occupy it completely. How to combine across bins? In the notes, you also have a lower bound for 0.7, and that tells you that no more intelligence is required. This is the best. One caveat, this is not the best algorithm. There are algorithms which can do better than this. One of them is called harmonic, it's part of the nodes. The best one is even more complicated. It's actually a variation of best fit. That's not part of it. There's a reference there. Interesting. Okay, let's start. Hmm. Very good question. So homework number 2 today will tell you randomization doesn't help for doing that income. So I've chosen every single homework to make sure that you get the nuances if possible. For ski rental, first and the second problem essentially capture the basic idea how to do the best randomized algorithm. We go beyond the worst case. Today's homework will make sure that you understand what this problem randomized number. So whatever lower bound you get for a deterministic algorithm, you should be able to estimate from that. So this is one problem where randomized algorithms are not studied. They studied many different variations of the parameter. People don't consider randomized algorithms. And somebody wrote a casual paper and then became possible. It is slightly longer. Correct. Okay. People feel free to leave. Have something else to do. We're going to say more detail. For ski rental, OPT, you tell. And always pays the cost of you know. A did not know that at all. L was some quantity which could possibly depend choice of two things. Whatever deterministic algorithm you chose for yourself, L could be chosen by the adversary dependent. Now we augment this A with some information L had about L. So A, in our classical setting, did not know anything about L. It only chose AK, to which it knows what the response of the adversary is going to be, and using that, he chooses his K. Now say A knows some estimate on L. If L hat was L, what would happen? First we'll go back to sensitive. Now suppose that L hat, I don't know how far it is from. Some estimate is given to me, I don't trust it completely. I don't even know what it is. It is, let's say, non-zero. Now what should be my objective? I have this extra information. One thing I can do is just ignore it and go back to where I was. So ignoring eta is what we did yesterday. Even if eta is available, I can still ignore it. We didn't do anything about it. We just ignored it. That's all. No. What we tried to do was minimize the competitive issue. Minimize Unity over key. Because I could index all the online algorithms as A1, A2, B. This is what the objective I was doing. I was ignoring this because I could always artificially create n equal to 1. So I was essentially completely ignoring. Now, somebody else is giving me this information without telling me what that eta is. Somebody told me eta, I can tune my algorithm to that eta. If it's very small, I will rely more on it. If it's very large, I will display it. What I'm not told is what is eta. Somebody is giving me L hat, but he's not telling me what eta is. Now I'm in trouble. If I use that L hat as ground truth, I might completely make mistakes. Because L could be completely different than L hat and I'm in trouble. Other thing is I could completely ignore it. That's another thing. In which case I go back to whatever my guarantee was 2. Because even after ignoring, the guarantee of 2 stands. It's after all worst case. Now I ask you, can you come up with an algorithm, single algorithm, which is close to OPT if eta is close to 0, without knowing what eta is? Somebody else is doing this eta for you. So if eta turns out to be close to 0, then your algorithm automatically should go close to it. Nobody tells you eta. All somebody is revealing is L hat. You have to use this information about L hat in such a way that if eta was small, I am close to open. And if eta is large, I am at least bounded. I don't increase my competitive ratio to input. So dual objectives suddenly come into picture for a single algorithm. You have to come up with a single algorithm because you can't create two distinct algorithms because you don't know what it is. So all the input you are seeing is L hat. All your decisions are going to depend on L hat without knowing. If it was known, we could do much more. There's another setting you can consider. Suppose the 60% you are accurate, then you could possibly come up with an algorithm which has a probabilistic variable. Here we are saying something more strong. I don't care what your eta is. If eta is small, I am close to opacity. Beta is large, I am still bounded away from, or I have a guarantee irrespective of what it is. So it's a imposing task for an algorithm. It's not that easy to think about, but it's turning out one after another. All the online algorithms are getting taken off. Theorem we know already. Will tracking we already. Caching tomorrow we'll see caching without this. Caching has been taken off. Lots of deadlines scheduling problems. So one by one. So it started only 2 or 3 years ago. While online algorithm based to 40, 50 years. This is a relatively new area. You can even think of any schedule. I don't know what you work on. Any scheduling problem you work on, you can think of this. Where you want to balance between a machine learned input, which unknown accuracy. How would you like to take out between when eta is small and when eta is large? All of this is open. Scheduling problems are like slightly nasty. When this. So even how to define this L hat is not clear. Sometimes here it was easy. So a single parameter input. So you can just simply define L hat. So it's the error. But in general, input could be very complicated. How do you even define the error between the estimated input and the true input? Sometimes that becomes hard. All right, any questions?
This time, as to why into is
Why E2 is? No, it is not a property. I'm just calling this bin input. Okay, this does an exercise. This is bad for fun. It will make my job harder to go back to the proposition with why it is. You can convince yourself.
on the 1.7 meter that
For best fit. For best fit, you will not be able to improve its analysis.
how
By creating a lower one. Top with the input, but this best fit cannot be better. That's the
the other algorithm can have better than
Yes.
what is there with 1.7.
So, remarkably, the first breakthrough improved the competitive ratio of the second decimal test. It went from 1.7 to 1.69. So it's a good breakthrough. Now we know something close to 1.57. So, if it's 4 by 3, then you bound. You cannot reach that. So details are in the notes.